started discussing on challenges in compiler design. So, there are several challenges starting with the language semantics to hardware platform, then operating system concerns, then the error handling, the powerful error handling will help in the will make the compiler more attractive. Then the debugging aids, that is if I want to rectify the logical bugs in the program, then how can I do that, how the compiler can help in doing it. Optimization, so we definitely want more and more optimization, but that makes the compilation process more and more difficult. Then the runtime environment management, so depending upon the facilities that we want to provide in the source language program, like whether it supports recursion and all, this runtime environment management will vary. And the speed of compilation, that is how fast is the compiler. So, it should not take lot of time for doing the compilation. So, if you look into the language semantics, so here are a few cases which which I would like to point out. One is that fall through case statement. In most of the programming languages, they will support some sort of case statement, and this case statement in some programming languages it is a fall through case, and sometimes it is not so. So, we can I can take an example, like most of the programming languages will have some sort of say switch statement, switch or case, and some expression, some variable or expression can be there, some expression e, and then we have got different cases. So, case 1, case 2. So, like that we have got different cases. Now, some programming languages, they say that depending upon the value of e, so it can enter into one of these cases. So, this is a case k like that. Now, if e evaluates to 2, so it will start executing from this point. So, what happens when it reaches the end of that particular case? So, we can have two types of option. In one option, it will skip the rest of the cases, and it will so if the switch statement ends at this point, then after finishing this line, so it will start executing from this point. In some other programming languages, so this is called a fall through case, in which once this case matches, value matches, then it executes that part and it continues. So, remaining cases are also executed from that point onward. So, it is just the entry point. So, it is like this, as if all these cases, they form a piece of code, a chunk of code, and you have got some entry points only. So, this may be the entry point for 1, this may be the entry point for 2, this may be the entry point for k, like that. So, after you have entered, so this entire piece of code will be executed from that point onward, until and unless there is a break statement in between, which will be taking it out of the case. So, but this is true for languages like say C, but in some other programming languages, so it is like this. So, this break is not there, but as soon as this is over, so instead of continuing with the next case, so it will come out of the switch block altogether. So, these are the two types of case statements that we can have in different programming languages. If you look into different programming languages, you can find them. So, naturally, the code that we generate for the two cases, so they are different, two situations or two programming languages, they are going to be different. So, another concern that we have is with say loop statement. So, loop statement, in some cases, suppose I have got a loop like this, say for I equal to 1 to 100, and in the body of the loop somewhere I have a break statement. So, suppose here there is if some condition is satisfied, then we break from the loop. Then what is the value of I when you come to this point? Okay. So, there can be different types of semantics, different type of logic about the value of I. Some programming languages say that when you are coming out with from somewhere in between without completing all the 100 iterations, so here you get the value of I which it had at that point of time. In some other programming languages, it says that no, I will be value of I is unknown. So, value of I may not be the value of I may not be predictable, it can have any arbitrary value. So, this way this loop index, so if the value may or may not be remembered beyond the last value, or even if this finishes properly, I it goes from 1 to 100, there is no break statement, then what is the value of I after the loop has completed? In some programming languages it will say that the value of I will be 101, some programming languages will tell that it is unpredictable. So, depending upon that the code has to be generated like that. Similarly, this break and next statement, they modify execution sequence of the program. So we have to take care of them. So, this way the language semantics, they have got they put many compulsion or many conditions on the code that we are going to generate. So, the next concern that we have is about hardware platform. So, code generation strategy for accumulator based machine cannot be similar to a stack based machine. So, in an accumulator based machine, what happens is that there is a special register which is called accumulator, and all operations that we do, one of the operands and the destination is the accumulator. For example, if you look into say 8085 type of architecture or 8086 type of architecture, all these architectures, so they have got one accumulator register A in 8085, and in 8086 we have got AX. So, there any operation that you do, so particularly for in 8085 architecture, so we simply say add B. So, add B means the operation that is carried out is A getting A plus B. So, the type of code that we generate, so it should be of this nature. On the other hand, the stack based machines, so what is assumed that is that, so there is a stack. So, whenever you do any operation, so this arithmetic logic operation, so they just pop out the operands from the stack, do the operation and push the result back to the stack. So, that way the code generation for this stack based machine is definitely different from the code generation for the accumulator based machines. Then this CISC and RISC architecture, so they also play a major role, like the CISC instructions, so they are more complex. So, we have got longer length instructions, complex instruction, they take different amount of time for execution, whereas the RISC instructions, so they are more or less similar, all the instructions are more or less similar in size and execution time. So, as a result, this CISC versus CISC and RISC instruction set, so they will also tell like what is the amount of what is the type of code that we generate for them. So, this way, and they have got many other features like the RISC machines, so they have got large number of registers compared to the CISC machines. So, naturally we will have more amount of the register usage will be more. So, optimization and everything will be different in RISC machine compared to the CISC machine. So, that is about the hardware platform. Operating system and system software. So, format of file to be executed is depicted by the operating system. So, so what happens is that we have got this operating system will be having the tool called loader, and this loader module, so it will be finding out it will have some specific format of the object file. Okay. So, this object file that we are having, so any compiler that we have, so it should try to generate object file in that format. So, otherwise the loader will not accept it. So, the program cannot be loaded into the memory. Then the linking process or the linker tool, it also has got a major role to play, because they will combine many object files generated by different compilers into some executable file. So, this linking linker tool, so it will also tell the acceptable object file formats. So, this is also there. So, of course, there are many different link file formats. So, normally linkers, they support a number of different formats, but anyway, so this code generation process will be guided by the this linking tool that we have. Then error handling. So, you have to show appropriate error messages. So, this is very important, as I told in the last class. So, for the user to understand and to appreciate that this compiler is doing a good job. So, the user may be asking for user may be looking for more meaningful error messages rather than syntax error a message like syntax error at line number 13. So, that is very very cryptic, and the user will not be able to do much with that. Or even if at least the line number has to be mentioned. So, if the line number is also not mentioned, then it may be a message simply that syntax error. So, syntax error Where is the syntax error that we do not know? So, that makes it difficult. So, they must be detailed enough to pinpoint the error. So, this error message that is flashed, so it should be detailed enough. However, it should not be very verbose to confuse, like say maybe the compiler tries to give 2-3 different options by which the error might have occurred. So, that way sometimes it is more confusing. So, so those things are to be avoided. So, this is actually up to the compiler designer to decide like what should be the appropriate error message for different types of errors, and that way the compiler quality will be judged based on the type of error message that is given. So, a missing semicolon may be reported as line number and then followed by semicolon expected rather than syntax error. So, if you give this expectation part, what was the expected symbol here. So, if you mention that, then definitely it is easier for the user to correct the program. Another example is like this: a variable may be reported undefined at one place, it should not be reported again and again. So, what I mean is that suppose I have got a piece of program where at this point I have got the variable y equal to x plus z, and I have forgotten to put this declaration of x somewhere here. So, this declaration should have come before the usage of x, but somehow it is missing, it is not there. Now, in some later lines also I might have used this x equal to say x plus p, that way x might have been used several more times in the piece of code. Now, so it is so once this at this point we have detected that there is an x which is undefined. So, we have flashed this message that x is undeclared or undefined, then there is no point repeating that message at this point as well. Okay. So, so if a variable is reported to be undefined at one place, should not be reported again and again. So, to handle this situation, what the compiler may do is that compiler may make a temporary entry into the symbol table with an indication that this is actually undefined, this is entered by the compiler. So, this accordingly the later part, so this when it searches the symbol table, so it will find x there, so it will not be a undefined variable. So, like that. So, this can be done. Then compiler designer has to imagine. So, this is the very important point that I wanted to emphasize. The designer has to imagine the probable types of mistakes and design suitable detection and recovery mechanism, and that is the expertise or experience of the compiler designer. So, what is the type of error that an user may make while writing program in a particular language. So, that has to be imagined by the compiler designer. And some compilers even go to the extent of modifying source program partially in order to correct it. So, this is similar to say the corrections that is done by many of the word processing softwares while we are entering the text. So, it does some it replaces the wrong words by correct ones. So, whether we like it or not, that is a different issue, but sometimes it is very helpful. So, similarly, when we are writing a piece of program, for example, if I am writing a C language program, if at the beginning of a sentence if I write fi, then most probably I am actually tried to write if and change it to fi. So, compiler can do this type of changes. So, it can change fi to if, and when it finds that there is some error, some error is occurring, then say fi. So, fi will be taken as a variable, and the variable, if it is not available in the syntax in the symbol table, that means fi is if fi is not a variable, in that case maybe the user has done a mistake, and instead of writing fi, if has written fi. So, this compiler can correct that fi to if. So, this type of corrections can be done by the compiler itself. So, that is one possibility. Then the other thing that we have is the help in debugging. So, debugging is suppose we have written a program. So, it is syntactically correct, but there are some logical errors in the program. So, it may so happen that in a program I am writing somewhere I have written like y equal to x by z, and we find that it is giving some result which is undesirable, and one possible so maybe we want to check at this point what are the values of x and z, so that whether the value of y is computed properly or not. Or suppose we have called a function x equal to f some function. Now after this function has been executed, we need to we may want to check the value of x to see whether the value computed is correct or not. Now apparently we can do all these things by introducing some print or write statements in my program at some intermediary places, but it is very cumbersome. So what the user can do, what the user can think about having a facility like I should be able to run my program line by line. After every line the execution should get suspended, and I will be able to check the values of the variables and then again give the continue signal, so that this execution continues. So this way the user needs to control the execution of machine language program, but sitting at the source language level. So the user does not know machine language level. So what is the translation of each and every instruction. So if the processor stops after every single program line execution, so that becomes difficult, but so that is of no use to the user, because user will not be able to track at that level. So user can track at the source language level. So that way we need to have some information where exactly to stop. So what you get is that if this is a source language program and this is the corresponding machine language program, then after every statement that we have in source language, I should so if this source language program translates to this much of code in the machine language, then after this I should put some additional information here, so that I can suspend execution at this point. Similarly, after this the next piece of code starts here, then after that there should be some facility, some code must be sitting here, so that I can ask the compiler, ask the execution process to stop at that point. So this is normally done by the help of a debugger, this stopping execution in between and all, but the compiler needs to introduce these codes into the machine language program. So that is very important. So compiler can help in the debugging process by providing this information in terms of that can help the debugger. Okay. So compiler has to generate extra information regarding the correspondence between source and machine instructions, and symbol table also needs to be available to the debugger, because debugger it will be the user will ask for values of different variables, and debugger needs to find out the offset of those variables, and offsets are available only in the symbol table. So that way these offsets will be used by the debugger from the symbol table. So symbol table is going to be preserved in this case, though previously we said that in the target code symbol table does not have any role, but here it has got some role. So for if the program is to be in debug mode, then this symbol table is useful. So this is particularly true when we have got initial phase of development. So initially in the program there will be lots of bugs, logical bugs. So that way we need to debug our program more, and once we get the confidence that my program is now logically correct, so I can remove all this debugging information, and then I can generate a code which will be running more efficiently. So this there are two distinct situations in which the compiler is made to run. In one case it is generating lot of debugging information and it does not do any optimization there. In another situation it does not generate any debugging information, but does lot of optimization, so that the program runs efficiently. So this debugging and optimization, so they go both of them are required in the program development phase, and the compiler should be able to handle that situation. So my compiler should provide these facilities. Then optimization, so naturally, so these are the series of transformations that may be necessary, that may be beneficial for most of the programs in a language. So the compiler designer must understand the general set of optimizations that are useful, the set of transformations that are useful for most of the programs in the language. So guessing this particular set is not very easy. Then the transformations should be safe in the sense that if I do some optimization, so it should not change the meaning of the program. For example, suppose I have got a statement like I have got a statement like say x equal to y plus z, and then at different places I have got reference to this x. Okay. So, at this point I have got a reference to x, say p equal to x plus something. So, then again at some point later I have got q equal to x into r. So, like that. Now, this x is a variable, so it is kept in the memory. So, if to in order to reduce the load on execution time, maybe we do not load this x from memory again, rather, so this x may be copied into some CPU register as well, and that at this point, so we take the value from the CPU register. So, that way it's one memory access is saved. So, if I have got multiple accesses to x in the program, so and if I have a register that holds the value of x, then that should be so we will save so many memory accesses. But the point is that the register that we are putting here remains reserved for the entire sequence. So, whether that is really the case or the register value can get modified due to some program execution sequence, occurrence of interrupts, etc. So, that may make this transformation unsafe. Okay. So, that the program may not work correctly under those situations. So, that is what it says, that the transformation should be safe. So, we should do optimize, but optimization should be safe. Then the trade off between the time spent to optimize a program and the improvement in the execution time. So, that trade off is necessary, but so the amount of time to optimize a program and if we want to do more optimization, it will take more time, but it will lead to more improvement in the execution time. Then there are several levels of optimizations are used. So, you can have, as I said, that there are different levels, we can do optimization up to different extents. So, we can have different levels of optimization, and as we go deeper and deeper or higher and higher level of optimization, the compilation time increases, but the amount of optimization that we get, the efficiency of the code, that also improves. And if we are doing some debugging, if we select a debugging option, so that may disable any optimization that disturbs the correspondence between the source program and object code, because optimization may change the sequence of instruction execution. So, naturally, if you are selecting debugging mode or debugging option, then all the optimizations are to be turned off. So, that is there. So, these are the various issues that we have. Then the runtime environment, so it deals with creating space for parameters and local variables. So, like say if I have got a piece of program, and at some point I am calling a function f with, say write x equal to f with some parameters, say a1, a2, etc. Then in the function f, I may have some more local variables. So, this is r1 and r2, these are the two arguments, and maybe I have got some local variables int, b1, b2, etc. Now, where are these a1, a2, r1, r2, b1, b2 stored? That is the decision that we take in the runtime environment management. So, that will be reserving space for parameters and local variables. So, for languages like Fortran, so this is done statically. So, we have got fixed memory address, memory locations created for them, from where it will take up all these values. Okay. So, this is this makes the compiler design process simple, but at the same time it creates difficulty if you are going to support recursion, because recursion, the same program may be called again. So, the previous locations which were reserved for R1, R2, B1, B2, A1, A2, etc., they will get overwritten by the new call and the new creation of the next instance of the call to the function f. So, this makes it difficult for supporting recursion. For recursion supporting, so we have to have some sort of stack frames, so which are more complex in nature compared to this static runtime environment management. So, we can we have to go for that. So, when you go to the runtime environment management techniques, so we will see that there are very efficient techniques that have been developed for handling this recursion. So, next we have got the speed of compilation. So, this is another important criteria to judge the acceptability of a compiler to the user community, that is how fast is the compiler working. So, is it in a flash of it is a flash, it gives the output, it gives the compiled output, or it takes lot of time. So, that way it is difficult. Okay. So, initial phase of program development, it contains lots of bugs, hence quick compilation may be the objective rather than optimized code. So, they are mostly we have got syntax error, then this logical bugs and all. So, there is no point doing optimization there. So, so at that time I should have an option by which I can tell the compiler, see, I do not want any optimization, I want the compiled code fast. Okay. So, that should be generated quite fast, or if there is any syntax error, that should be reported fast. So, that part that is the initial phase of program development. So, we will be looking for the compiler to work with the high speed of compilation. Maybe we forego the optimization part. But when we go to the towards the final stages, execution efficiency becomes a prime concern, because there we are ready to spend more time, but we do not want the code generated to be inefficient. So, that the code has to be very efficient. So, we want to spend more time on the compilation process, but we want that the output or the outcome of the compilation, it should be very efficient, the code generated should be very efficient. So, this is towards the final stage of compilation process, we want optimized code. So, for the same compiler, sometimes we want that it should be running very fast, sometimes we will want that it should be it need not be that much fast, but it should generate very efficient code. So, these are the issues that we have with the compilers. So, the compiler designer should look into these angles. So, not only the code generation process, but this entire other issues are to be looked into, and that makes the compiler design process complex. So, rather than so if we do not bother about all these concerns, then it is pretty easy. So, we have got automated tools by which you can generate the code for some processor, but as soon as you bring all these concerns into your purview, so this entire code generation process becomes difficult. So, in our course, so we will try to look into these aspects again and again in different chapters, and that way it will go. So, at the end we should be able to design compilers within a reasonable amount of time and taking care of all these issues.